this talk will focus on pairings over elliptic curves defined over finite fields. So first of all, what is a pairing? So with the word pairing, I mean a map from the Cartesian product of two additive groups to a multiplicative group. And this map should be bilinear and non-degenerate. So if we want to use a pairing for a practical application, the pairing is required to be efficiently computable. Unfortunately, efficient pairings are provided by elliptic curves over finite fields. And for example, the Weil pairing and the Tate pairing are two standard, traditional, I would say, pairings over elliptic curves. And more recently, some alternatives have been proposed, like the eta pairing, the Tate pairing, and their modifications. And choosing the right pairing depends, of course, on the specific scenario. So the question is, what are the groups G1, G2, and GT in elliptic curve pairings? So in order to answer this question, I have to recall a standard result about elliptic curves. So suppose that FQ is a finite field, E is an elliptic curve defined over FQ, and R is a natural number which is relatively prime with Q. Then we denote by E of R the set of all points on the elliptic curve E, so all points P, such that the order of P is divided by R. And the nice thing is that we know the cardinality of this set and also its structure. I'm talking about structure because actually this set is a subgroup of the group of the elliptic curve, which is called the R torsion subgroup. And its structure is given by the fact that it is isomorphic to ZR times ZR. So elliptic curve pairings consider G1 and G2 equal to one R torsion subgroup, and then GT is the multiplicative group of an extension field F Q to the K, where K is the embedding degree of E with respect to R. So K, this embedding degree, is the smallest exponent such that all the coordinates of the points in E of R are contained into the extension field F Q to the K. And for efficiency reasons, it is standard to consider R, so the natural number R, as a prime number, and then G1, G2, and GT are prime order groups, and the order is exactly R. And so G1 and G2 are two subgroups of order R of an elliptic curve, and we know how many of these subgroups are available since we know the structure of this E of R. And in particular, we have R plus 1 of these subgroups, and G1 and G2 are chosen differently in such a way that the pairing does not always output 1. So elliptic curve pairings were initially used in cryptography for cryptanalytic purposes. But then, since the seminal work of Antoine Jou in 2000, they have been also exploited to construct new crypto systems. And most of the time, the security of these crypto systems is guaranteed as long as the discrete logarithm problem is hard on each of the groups G1, G2, and GT. But cryptography is not just a matter of security, it's always trying to find a balance between security and efficiency. So let's do a simple observation. So if the embedding degree k is equal to 1, then this means that we can take G1 and G2 both on the base field FQ. But now this is probably not the best option, because Q must be really big in order to have a difficult discrete logarithm problem over the finite field FQ. So having a big Q means that both the computations on G1 and G2 are quite slow. So if we have an embedded degree which is bigger than 1, then, of course, one of the two groups, G1 and G2, must be over an extension field, which is not a great thing, but we can consider a case where G1 is defined over the base field. And in this case, the base field is not as big as in the previous case. So scenario 1, k is equal to 1, and G1 and G2 are both over the base field, which is big, so slow computations. While with k bigger than 1, only one group is defined over an extension field, which is problematic, but then another group is on the base field, and this time the base field is not too big. So in terms of efficiency, we want to work with elliptic curves for which the embedding degree is bigger than 1, but it's not too big. And this is translated into the following conditions. So G1 is set to be the only subgroup of a certain prime order R of an elliptic curve E, a suitable elliptic curve E that has this property, while G2 is any possible other subgroup of order R of the curve E. So I hope that the discussion in the previous slide explains why we use the word pairing-friendly elliptic curves. So pairing-friendly elliptic curves are curves that admit a large prime order rational subgroup, and at the same time their embedded degree is different from 1, but it is small. And one might ask if it is easy to find pairing-friendly elliptic curves, for example, just sampling in a uniform way or in a random way from the set of all possible elliptic curves. And the answer is not. It's not possible to obtain pairing-friendly elliptic curves in this way, because they are far from being common. And this means that in order to obtain pairing-friendly elliptic curves, we need ad hoc constructions. And many of them have been proposed in recent years, like, for example, BN curves, Freeman curves, and in our work, we focused on BLS curves. So when pairings are used for identity-based crypto systems, there is often the need to efficiently hash to either G1 or G2. So an identity-based crypto system is, for example, a crypto system using as public keys binary strings, so like strings of information, like an email or something like that. And hashing to the two groups means that there is an efficient map going from the set of strings to the groups, G1 or G2, which looks random, so a pseudo-random function. And one might observe that there is an easy solution to this problem. We can just pick a generator of the target group, and we consider random multiples of this generator. But this is not a good solution, because the points that are produced in this way, for all of them, we know the discrete logarithm with respect to the generator P. So this is not an acceptable solution. We are looking for something different. And in our work, we provided some efficient hash maps to G2 on BLS curves having embedding degree in a set of 5 elements. So we consider the embedding degree equal to 12, 44, 30, 24, 30, 42, and 48. So I don't have enough time to give many details about these hash maps, but I just want to say a few words about one specific case. So the case for k equal to 48. So first of all, I need to say something more about BLS curves. So BLS curves are ordinary elliptic curves, and it's possible to construct ordinary elliptic curves with any embedded degree. But for efficiency reasons, we consider just embedded degrees that are equal to 0 mod 6. And for each fixed embedded degree, the BLS construction provides a family of elliptic curves over prime fields having this embedded degree as having this fixed k as embedding degree. And this family is parameterized by 3 polynomials, one for the cardinality of the base field, which is a prime field, one for R, the order of the groups G1 and G2, and one for the number of points of the elliptic curve over the prime field. So to be more concrete, every time that we evaluate these 3 polynomials on an integer x0, we obtain 3 integers p, r, and t, and then if we use them as input of the complex multiplication method, we obtain an elliptic curve E defined over fp, and this elliptic curve has the properties that we were looking for. So it is defined over fp. The number of points of E over fp is equal to p plus 1 minus t. This number is divided by r, and the embedded degree of this elliptic curve E with respect to r is k. Okay, now how to hash into G2? So the standard method is just to compute a random element p in the extension field fp to the k, and then multiply it to force, so multiply it by a scalar to force this point to the subgroup of order R. So this scalar multiplication is by a cofactor, which is the cardinality of the points over the extension field f p to the k divided by R, since we want points of order R. And the point is that this cofactor is usually quite big, but we have also good news. So this cofactor can be parameterized as well as a polynomial with rational coefficients. And we can also exploit an efficiently computable endomorphism psi, which is, as I said, efficiently computable for every BLS curve. And furthermore, for every point in on G2, we have that this relation holds. So there are currently 2 methods to speed up the computation of the scalar multiplication, so C times P. So we said that C is quite huge, so it's expensive to compute C times P. And one method is due to Scott et al., while the other method is like an improvement due to Fuentes et al. So the main observation of their method is that instead of computing C times p, we can obtain a multiple of this c times p, and this multiple is fine as well. And in particular, they proved this theorem, saying that there exists a polynomial h of z, such that if we evaluate the polynomial h on the efficiently computable endomorphism psi, then h of psi applied on p, where p is a point in G2, gives a multiple of Cp, as we wanted. And we have some constraints on the degrees on the sides of the coefficients of this polynomial. And the nice thing about this theorem that the proof is constructive, and so it gives an algorithm to actually compute this polynomial h of z. So this polynomial h of z can be parameterized as well, and this makes its coefficients polynomials with integral coefficients with the unknown x, and also some constraints on the degree of these polynomials. But it's true that we have an algorithm to compute this polynomial, but it requires an expensive execution of the LL algorithm, and in particular, the cost of this execution grows with k. So we weren't able to apply this algorithm to BLS curves when k is equal to 48, but we were able to provide by theoretical means an alternative polynomial, which is not the one that should be output by the algorithm that we saw in the previous slide, but it's a polynomial that is good as that one, because it is such that h of psi applied to p gives a multiple of c times p, and also the coefficients satisfy the same constraints on the degree. Okay, so that's everything from my side. For more details, I refer to the paper, and I just want to finish this presentation just saying that I'm really proud that Michele Elia was my supervisor, and I'm a bit sad that the last time that I met him was for the UMI conference in Pavia. So that's the end of the talk. Thanks a lot.